Okay, so I'm Mary Thomas. Thank you all for coming. Today I'm going to talk about interactive high performance computing. It's a special area where you learn about, what you want to do on a supercomputer or a cluster or some high-end resources and what it means to be interactive. So I'll talk about that, and hopefully by the end of this session you'll have an idea of the reasons for doing it, the reasons for not doing it, and the kind of tools that are currently available. And so I've got a couple of links in this slide. One is a link to the homework that comes along with all the complex materials. It's a hands-on markdown file where you can literally, you should be able to cut and paste some commands and run them on expanses where I did a lot of my development work, although these concepts would apply to any HPC system. And in the world of HPC, if you're working on HPC, you know that often things change. So the caveat is they all worked last night. I try and test like right before I do this talk because things do change. And you're learning that as you take the complex material. So the complex program is a new idea thought up by Bob Sinkovits. His idea is that there's just all these people who are doing really advanced science, but they're not programmers. They're not developing the parallel code or the GUI application. They're using it for really important work. So let's develop a training program that focuses on that cohort. And that's what this talk is part of, that whole series of complex materials. And the GitHub is in the repository for my talk is in the GitHub repo for complex. So we're posting that link during the talk. So in this talk, basically, I'm going to talk about, what do we mean by interactive high-performance computing and how it compares to standard HPC, batch computing, and then the interactive computing and features. And then I'll show you how to do this on Expanse, how to get on and get an interactive node, and talk a little bit about what you can do. And if you want to run GUIs, you need to use something called X11 forwarding. And this gets a little tricky, but it's something you'll need to learn about. And then interactive applications, examples from viewing data to visualization platforms, and then gateways and portals. And we'll end and spend the last minutes of this talk getting you guys onto the Expanse portal if you're set up for such a thing. So typically, you can do a lot with a supercomputer. You can do fluid flows, you can do bioinformatics, you can do solars, like you could probably take a great picture of a solar eclipse. There's a lot of physics and science that get done on these supercomputers, but they're tremendously large. By the time you get onto a supercomputer, it's too big to fit on your laptop. And so, large things can get done, but it also requires a lot of infrastructure. But you might want to interact with your data, or you might want to even interact with your application. And so that's how the concept of interactive computing came along. So you have to run your jobs on these clusters. HPC clusters are powerful. You can get on there and run some tasks and jobs from the command line, CLI, if you haven't heard that term. You can submit jobs to a queuing system that will figure out for you what nodes your job should run on. And that's an optimal way to run. And then you could have clients like PyTorch or other applications, and we'll talk a little bit about that. And jobs scale from one core to hundreds of thousands of nodes depending on the machine. And for large jobs, schedulers are needed to figure out when you come onto the system through some kind of switch and scheduling system, which of these thousands of nodes and cores do you need, or hundreds of nodes and thousands of cores that you might need. And schedulers are great for figuring that out. And so if you have really large jobs, you're most likely going to run that through a scheduler. And Marty did a great talk on that. I think it was 2 weeks ago. So we do have a webinar on batch scheduling, and we have more about running jobs coming up in the complex architecture. So HPC systems are a little complicated. They have a complex architecture. I'm not going to spend a lot of time. Bob kind of went through that for HPC systems in one of our early webinars. I've been working, and my examples run on Expanse. Those are just some of the computer racks of Expanse. It's liquid cooled. It takes a team to keep it running. And if you find that complicated and challenging, that's okay. We expect that. It takes several years to get to know HPC systems, and then you want to get on there and do something interactively. So understanding, though, all the architecture behind what you're trying to do helps you debug things when they go wrong. What's interactive computing? It's somewhat related to, well, batch jobs replace interactive computing. So when you're trying to run a job, you get on and you can get onto the computer through a terminal, and you're typing on the terminal. And from a computer science perspective, anything you do on a computer, like your laptop, and you type and hit a key, you're doing interactive computing. But when it's on your laptop, it's not really high performance computing. You're opening, and you have 85 windows, you have all these applications running, and those are interactive but not high performance. So the niche area of interactive real-time computing is when you're on one of those compute nodes, one of these guys here, right? There's compute nodes on here, and they're sandboxed away from public access so that they're protected. When you get onto one of those, you're interactively working on it. Most of the time, you'll put your job together and use a service called the batch service, and you give it a script that says, run this job on this many nodes, I need this much memory. You kind of outline and give a map to the system for what you need, and it goes and looks and it figures out, okay, I'm managing all these resources, and I'm going to put some jobs in these queues. We have these different partitions, and the jobs queue up and they run when the system finds a good match. It's not FIFO and it's not LIFO. It's in between. There's intelligence behind your job, and if you have to have a lot of nodes, it may have to dry up some nodes. So the coming in through the shell and using the batch job to submit, when that happens, then your resources will get allocated, your job will run, and you'll get some output, usually in a file, usually the same directory where you submitted the job. And you can also run jobs through the portal, and it will submit jobs to the batch queue for you as well. And that's also considered interactive in the sense of you're running and submitting jobs to the system. And then there's Jupyter Notebooks, which are also a form of interactive computing, and interface to, you can run them on your laptop, and we also have ways to run them on a large system like Expanse. But generally, when you submit the job through the batch queuing system and through Galileo, I'll talk about that quickly today, you can submit a request to get an interactive node, and it will launch your Jupyter Lab where you can access and run your Jupyter Notebooks. So that's considering interacting with the high performance computing node, but the way you did it was through batch jobs. There's also ways to directly get that node and type on it through your terminal, and I'll give examples of these all through the talk. So HPC batch computing and then interactive computing. So I'm having a problem with this bar here blocking my titles, but I don't know what to do about that. So this one is the batch systems, more about batch queuing systems that I started talking before. We usually just call them batch systems, but again, you queue up your jobs, you run your job, but your job gets launched by the queuing system, and it starts your job, and then whatever you put in your code, that begins to execute once you get your systems. And it includes these features of a scheduler, the queues like on Expanse, these partitions, and then the kind of job that you might be running. And you want to get an idea of the features of your job so that you ask for the right resources. You don't ask for 10 hours and 100 nodes when you just need one core on one node for 5 minutes, because it also costs you. You have these service units that are assigned to your account, and you only get so many. You have to justify them because Expanse is a national resource that a lot of people want to use, 6,000 plus users and growing right now. And so we want to make sure you get what you need when you need it, but you get it in a reasonable way. You don't, and so, you also have to have permissions. And so you know how batch jobs work. And if you don't, go to Marty's presentation from last week. So the main goals are to the queuing systems job is to look at the thousands of requests that might come in on any given day and minimize the time between job submission and completion for a user. We don't want that. To optimize the utilization of the CPUs. Again, we don't want a user asking for 10 nodes and they only need one core on one node. So we optimize that so that it also checks for job requirements, and then maximize the job throughput, run as many jobs as it can, and have the back-end infrastructure for that, and support running these jobs automatically in the background. And then to wrap up, finalizing the job information so you know what happened. And so simple architecture, user goes to the login nodes, runs the job script, submits jobs, and then it gets put into the batch system. On Expanse, we have the Slurm resource manager, simple Linux utility resource management, and yes, it is named after that drink from Futurama. And again, we have the scheduler system with all of its services that you access through some black boxes between that, and then once your job is approved and running, it goes onto one of these compute nodes. So let's see. Okay, so scheduler does asynchronous scheduling. This is a little cartoon I like that kind of gives you an idea of how the scheduler works, and that it places jobs in these queues, and it tries to anticipate when jobs will be done. While the longer jobs are running, it backfills in these little jobs. So that's its job, to make sure that things are optimized. Okay, so the next slide talks about interactive computing. Okay, so interactive computing, like I said, is when you do type on a keyboard and you're interacting with whatever computer you're on, your laptop or through a terminal app on my Mac. I can log on to a remote computer, but that's all interactive, but it's not high performance computing. It's not using high-end resources. And so for interactive HPC, instead of having a batch job running your application for you on launching your application and letting it run on a node, you get that node real time. You can log directly onto it. You can enter commands directly onto it. And you can perform tasks like running some application that might take up a lot of memory, and the node is good enough for that. But if you did it on the login node, everyone would be really unhappy because you used up all the memory on the login node. We don't want you running GUIs like MATLAB or R or notebooks on the login node. We want you to get an interactive node and run it there where you have the resources that you need, and we have the resources where we can support you. So it's used for things like code development and compiling. Big models can take a long minutes, 30, 40 minutes, or even hours to compile. And if you have a large data set, you have a low memory, simple application, but a lot of data, you need to get the data staged onto a node, and you need to have the right I/O. And then if it requires user inputs like notebooks, MATLAB, RStudio, and other GUIs, we support those on Expanse. If we don't, reach out to us so we can look at supporting a GUI that you might need. And so the actions performed on the node are a result of the user input in particular. So this is user interactions with the computer. So you have these compute nodes here, and you get some kind of access to the system through what we call a head node, a login node. And the login nodes, we have 2 on Expanse, and these are shared by everybody. And through Slurm, for example, you get one of these nodes. And when you get that node, all the people over on the login node, they're not able to access that node. You own it, in the sense of you can log in directly to that node, or your application will get launched on that node. So you've got all the power of that node dedicated to you. And this is an architecture that's using reverse SSH so that you can directly connect. We have all of that deployed on Expanse. You don't need to worry about it. Okay, so interactive computing motivations. You need more memory, you have too much data, or your network's too slow. A lot of people end up going to a cluster like Expanse because your jobs don't fit on the system you're using. And so then you have to grow into this bigger system. At the moment this slide was made, we have 768 nodes with 128 cores per node and 2 gigabytes of memory on each node. My MacBook Pro has one node with 8 cores and 16 gigabytes. So it's much bigger, and getting on there is great. Your code will run, but it is a little complicated. But anyway, if you get a node, a single node, you can interact with your application like you did on MacBook Pro mostly, but you'll still be able to get on it, but you have more power. So if you have too much data, you'll need to put your petabytes of data onto the Lustre file system. Then you need a good network to move that data in and out. SneakerNet won't work, and Ethernet won't work, but you need something more powerful. And we've got high-end networks inside the Expanse architecture. And your home network is too slow. That's another reason to be moving to being on Expanse and doing HPC. But you can still interact with your application like you did on your other systems. So the methods to interact with applications. So you might interact with your data after the job is done. And there's a lot of different ways to interact with your application and your results. For your data, there's all these Unix commands that you can use to access grep, awk, sed. How many files did you output? That's interacting. It's not high end, but it's still looking at large files, for example. You need to find out what you've got. You can look at the contents of your batch job or your raw data. You can do a data browser, and I'll show you an example of that. You can plot your results. If you had large file and you were using a high-end visualization system like ParaView, it could look through your gigabytes of data, or I don't know about peta, but terabytes of data, and you could selectively pull data out and plot it. That's a really good reason to get an interactive node. So accessing big data sets with high-end node features is a good reason. And again, visualizing your results. You can also view your data through using APIs like NetCDF and HPF. And then data analysis platforms like MATLAB and R, and running your notebooks. So interactive notebooks, Jupyter, everybody knows about notebooks now. It's very common. The last few years, they've just exploded. And in my mind, when I saw my first notebook, I went, wow, I'm inside my code. I loved it. It felt real natural to me. And so there's different instances like the Jupyter notebook. This picture up here is installing Anaconda on my laptop, and I have a lot of features. MATLAB is also an interactive application that we support and requires, customized installations, but we have parallel MATLAB on Expanse. Jupyter architecture for, this is on the Cori system at NERSC. And then over here is an image of ParaView taken from Amazon Web Services. Okay, so another interactive tool is the Expanse portal. We'll talk about that in a little bit. It's a web-based application, and the team has worked really, really hard to make it easy for you to do batch script job submission, Jupyter notebooks, and run MATLAB and RStudio. And so we'll talk about that. And once I get done with part of my talk, you'll go, wow, just put me on the portal to make it easier for me. So the interactive tools provide access to HPC systems. Oh, there we go. I got rid of that bullet. So they do have a vulnerability. They provide access to the HPC systems, and often over HTTP. So this is something we talk a lot about, and we have a tool for that, and I'll talk about it in a moment. But by default, I want you to realize when you first launch a notebook, if you do it by default, it's HTTP. on your laptop, maybe that doesn't matter, but it's just a gateway. It's an open door to your accounts. If somebody got that URL, they could potentially do something malicious. So we have a wrapper application called Galileo that uses a proxy service, and you get an HTTPS connection, so your connection is secure. You still don't want to give away the URL, but at least the signals across the wire are secure. So make sure when you pick an application, you're being secure. Now, we like to think Expanse is pretty well sandboxed so that only your account could get hacked, but we don't want anybody getting hacked. All right, so how do we get these HPC nodes? That requires a little bit of work. You would use it if your application, like I said, is interactive. You need to stage data. You're running AI applications are very interactive, or you want to compile large complex applications that take a long time. So you can run two kinds of commands using the srun command that you get from the Slurm scheduling environment. And you would want to either be on a CPU, or you could directly get a GPU and have an interactive node. These two commands are in the Expanse user guide, and I tested them. They worked last night. And they're in the GitHub repository interactive computing repo markdown file, so you should be able to cut and paste these. Just make sure that you put in your account, not mine. And these should run for you right out the gate. I say, but sometimes copying and pasting can have a problem. But I've tested them and they work. This is the example of asking for an interactive node on the GPU. And I have CP up here. Sorry about that typo. But here we're loading in, and I'm going to run so I've run this command. And what happens is when you launch that scheduler, the Slurm scheduler, starts looking for a node for you. I get a job ID, and then I have to wait sometimes not long, and sometimes it can be 10 minutes depending on how busy the system is. But I've got an allocated resource, and you can tell you're on a node when you see that the node ID, this was login 1, and now this is Expanse 955. That is a compute node. And I'm already on it, I'm logged on. So now I'm going to configure my environment using the modules. And I'm going to run from the command line a parallel model called MPI prime. And it runs and we get an answer. So this is an example of running a parallel C code on a login node. This won't run on the command line of login node because it doesn't support parallel job running. MPI doesn't run on that. We don't want you running parallel jobs. So anyway, this one runs from the command line. So you could get on a node, compile, debug, and test a small version of your code, and then go, okay, it's working now. I'll run my big jobs. I'll submit them through Slurm and get 1,000 cores and run my job that way. But this is a good example of test and develop. Here is another one going for a GPU. And how do you know you're on a GPU? You need to be able to see the NVIDIA-SMI. And you want to make sure that you're on a GPU node before you try and run your code. So this is a little hint for you to be able to tell when you're on the GPU node. Okay, so now that we know how to get on the nodes, we can do different things. And one of the biggest motivations, probably if I got a number from the sysops people, is they're launching Jupyter notebooks, but that's not necessarily the case. R is very popular, and MATLAB those are two very popular GUI-based apps along with Jupyter notebooks. So you want to be able to launch them from the command line, like run Galileo or launch MATLAB, for example, not Galileo. You would do that on the login node, sorry. But you need to be able to do something called X11 forwarding. So you have your client here, and you want to be able to see something that's a visualization that's being launched and run, like ParaView or MATLAB on Expanse, for example. And it's going to make an image, a GUI. And so you have to use some particular protocol to exchange that data, and that's called X11. So you have to set up permission on your client, permission on Expanse, and permission in your connection. And it's supported on Expanse, but for example, sometimes your laptop doesn't support it properly. Like I upgraded my Mac OS to its latest Ventura, and it has an X11 problem. And this is like a big reason to use the Expanse portal, because it already runs most of the apps you need. And if you have a GUI app that you want, maybe we could get that integrated into the portal if there's a community that needs it. But if under normal expanses, you just install Mac OS Quartz, and then you use the -y flag, which tells the SSH system to go ahead and authorize X11 protocols to exchange GUI images, for example, basically. And I installed it using Brew. So this is an example of how to do this. You have to make two windows. One window, you set up a connection, get your interactive node, so you own that node, and then you have to be logged on to Expanse, and you use the SSH-Y directly onto that node. Now you're logged onto that node and you're supporting the X11 protocol, and theoretically you should be able to launch MATLAB. And indeed, I've done it in the past, but it's not working today. So, I won't do a live demo, but I was in the past able to do something simple like GNU plot. For those of you who've been around a long time, GNU plot is a workhorse. It's been around for 40 years. It's a very simple way to analyze data really quickly without a lot of overhead, not a lot of memory, but it is a visual output, and so you want to run that on an interactive node. 99 times out of 10 it works, but this time, because of my Ventura problem on my Mac, it doesn't, but for you it might work. And it's a great way to test if your X11 protocol is working. You just open up GNU plot. These are the modules that I needed last night to run GNU plot, and type plot sine x, and up should come a sine x plot. You can also do a lot more with GNU plot. So if you can get that to work, great. That would be fantastic. Okay, so another way to view data. Not all data sets are really simple and linear. They're usually high-end, high-performance, large-scale data sets are really complicated. And one of them is the NetCDF, Network Comma Data Form. And also there's the HDF, high density format. And they're actually objects, and they have information in them that describe the data and have metadata about the data inside the file. And so NetCDF, you can use it on Expanse. Again, because I couldn't get X11, I can't show it to you live, but you can view some data and then plot the data with NCView, and you could use something called NCDump. And the same with HDF, they'll have similar toolings. So I'm not going to go through all the configuration information for that. The steps are in the talk, and it may have changed depending on where we are with what you need to do in the module support. If you don't know what modules are, go back to like our Expanse 101 or our introductory webinars to teach you about the module environment. It's a great way to simplify how you configure your working environment for what you're trying to do. For example, to use NetCDF, I need one environment, one set of libraries that would be different from ParaView or running MATLAB. And so you can customize that environment. So these slides just sort of show you what those variables are to put in your bash script, for example, to do the module load. And then NCDump is a way to view what's inside of a file. So this is a list of a couple of the NetCDF files. There's the help file, and for example, here is NCDump of some simple data generated by a simple file. So here you see that metadata. It's really powerful to have that with your data. That's why having something like NetCDF or HDF is, the motivation is complicated to get it going, but once you understand it, all of your data has the metadata, so you don't have to keep little log files or text files about the data that you're outputting. If you can use NetCDF inside your code. It runs in Fortran, C, C++, Python, and so does HDF. I think HDF is a little more updated, but it allows you to have this metadata with your raw data. And down below here, there's just like 100 lines of real data, but I know what my data means, and I can read that at the same time I'm reading in my data. So I'm not trying to scare you away from it, I'm just trying to show you it does have value. There you go, there's all my density, and I know what the calibrations. I could even put in here metadata about the scaling factors, whatever you want for the metadata. So that's the power of using something like NetCDF. All right, and you can also visualize your data right there, real time, maybe even while it's being dumped through some kind of backup mechanism. Okay, so those are really good examples of interactively viewing your data. So then there's programming platforms, MATLAB, R, and notebooks. So here's MATLAB, runs as a GUI, and you could run it through Expanse, or you could just run it through the command line. But this one needs the right connection. So this is an example of when you don't get it. But I'm putting in here, use the Expanse portal. I feel like a running advertisement. All of this stuff here works, and if you need to use it, here's examples of how, and SDSC help desk people will help you get that done. But if you can do it through the portal, please do. They handle all of these special SRun. Galileo does that for you. It sets up all the right memory and protocols. It's really easy, so we'll make sure, I want to make sure we have time to get to that. We have an hour and a half, so I want to make sure we get to that. But this one just sort of summarizes everything I did with that two-step for launching MATLAB. And so there's MATLAB that was running, I think, on for me on Expanse. I'll go down into Jupyter Notebooks more quickly, but R, it's the same thing. This is on TSCC. I don't believe Expanse at the moment supports R from the command line, but TSCC does. It has a special command that gets you R on the command line. And I think that they have a portal, or we're working on a HPC portal for them as well. All right, so notebooks. So Jupyter Notebooks, we all know what Jupyter is, and it's like this API that allows you to get inside your code and navigate it. And it's so exciting to make a few changes to your equation and watch the results change. You can imagine, though, this wouldn't work on petascale data unless it's a particular architecture, but for modest-scale data, it's great. You can access them on your laptop. There's a lot of ways to install Jupyter, but we want to make sure you're using secure notebooks on the SDSC systems, like I mentioned earlier. You want to always make sure your passwords are protected and your connection is protected, however you're connecting. So locally, you put that on install Anaconda on your laptop, and remotely you can install it, but we don't recommend that. You can install Anaconda on Expanse, but it takes a really long time. It takes up a lot of your disk space that's assigned to you, and it uses up a lot of resources, and you don't need to. Marty Candace, he's at this meeting, so you can ask him about this. He and the user support people, Nicole, Mahi, they all work very hard to make sure whatever you need is in our standard user-supported paths to libraries and binaries and executables, so you don't have to go through all of this. If you want to run remotely, typically HTTP is the default. You can connect using SSH tunneling, and that works. It's inconvenient because SSH tunneling depends on a port being open on your laptop, on Expanse, and on the compute node that you're grabbing, and those come and go. And sometimes they just time out, and so it's not convenient. What we want is for you to have something stable, and we've developed the satellite reverse proxy service and the Galileo client. Well, most of you have probably already used it. Galileo is awesome. You log onto the Expanse node, you type a simple command called Galileo with a bunch of arguments to it, and you get that secure URL, and you just wait a little bit, and you'll have your notebook running on a secure HPC node. And we'll talk about that. And he's got a great web page that describes it. And we have a webinar on it, I think, as well. So you can launch these Jupyter services at SDSC using Galileo, and you can run it on CPUs and GPUs. Treat the notebook URL like a password. Don't give it away. It's a direct access to your account. And again, we've sandboxed your account, but your account itself could be vulnerable. So I won't go into too much detail so I can leave time to actually get onto the portal. This is details about Galileo and its features. Basically, there's all the features there, and you submit your command. And what we've added is when you submit Galileo, you get a URL, you enter that URL into a web browser, and what you'll see is a status window that the green dots will tell you it's in the queue, which means everything worked well enough for it to go into the queue. That's a good thing. And then we're waiting for the queuing system to find your node. Then once it gets the node, some other things have to be built in, network connections and things. So it's running, it's getting mapped, and then it's ready to run. And up will come your connection to Expanse, and mine defaulted to my notebooks. That's Galileo in a nutshell. So you call Galileo, and it's very simple to set up a link to Galileo, and it makes it easier for you to run your jobs. So you can run Galileo from the command line. First of all, make sure that you can find it, and so you set up a path variable. Excuse me. Sorry about that. My local street people decided to do some digging, and I had trouble hearing. Okay, so anyway, you've got, you're going to use this Galileo launch command, which it comes right out of Marty's web pages. Make sure you put the right account in there, and then this should run. You'll get a bunch of stuff out, and it says, oh, the job script, whatever you had in the script is good. It's going to be submitted to Slurm. Here's your Slurm job ID. You can monitor that running the SQ command. And you get a URL, HTTPS. That's what you cut and paste into the web browser. And you'll get your status on that. And then eventually your notebook is launched on a GPU or CPU device. Sometimes when you log in and you ask for a notebook, you may land in a different directory. You can navigate around. Marty has an argument in Galileo where you can tell it what directory to start with. But remember, we asked for Jupyter Lab to launch, and that's what got launched. Okay, so we have some training example notebooks in our GitHub repository. And you can grab some of those, the simple ones, and see if they run. Okay, so now we'll have plenty of time now to get to the portal, yes, and start working with that. The portal is rich with features. In my talk, I have a bunch of slides because live demos sometimes don't work, but I actually want to try and get everybody to try and log on to the portal. But when you log, you'll come into a landing page that lists all of its, some of its capabilities, right, in what they call pinned apps. But there's also a navigation bar up at the top, and you can look at active jobs that are running. You can launch MATLAB, RStudio. You can look at your home files. You can build a job, and you can launch a Jupyter notebook. And so the nice thing about the portal is getting logged in. Once you're in, all of these command line things I showed you above, you can bypass all of that. So simplify, use the portal, use it as much as you can to make sure things are working. And then if you need to go bigger or you have a limitation, talk with user support, communicate with them. and see if you are going to benefit by going to the command line environment. There's all kinds of scenarios, so I tried to cover them in this talk, but again, if you can use the portal, it's a good idea. So here's a file browser. Let's see, yeah, file browser. This one is launching MATLAB. You have a few fields to fill in a form. Once that's done, the workflow is you identify, I want to launch MATLAB. I'm going to fill in some forms telling MATLAB, telling the system what partition I want, the number of hours it's going to run, what my account is, things like that. Then the system takes that request, bundles it up, and submits it to the batch queue, the portal system, and then you get information about a pending job. And when it's ready to launch, you get a clickable link that allows you to launch it, and MATLAB, the interactive GUI, will show up on your laptop screen. So again, maybe a little work at the beginning figuring out, well, what do I want for my to get the job I really need. And then once you do that, repeating is really straightforward. And launching notebooks, the same thing. There is a Jupyter session input forms. Now, what I did was I took a template for all the form input elements and put them into the GitHub repository. Down at the bottom, you'll find that. A simple one that works, or it worked for me last night. And when you submit this the same way, your request gets bundled up, and then through the portal software in the back end, it sends the request to the scheduling system, and eventually up will come a link to your Jupyter. You'll get this link here, and then you can go wait for it to all get fired up, and you'll be running the Jupyter notebooks. All right, so this is the input data. There's so much of it, I just wanted to make it easy for you guys to grab it and make it go. One of the things is we've learned that using containers on a GPU is very, very helpful. You can try, but the environments can be so complicated that what we found is create some containers that run and have everything built into it. And these containers are maintained by our systems people. And so they're always working. And so use a container. It makes your life better because you don't have to worry about libraries and modules to a certain extent. And if it's in the container, if it's not, then you can work with the team and see if it could be put into the container. And we have a lot more than just this one, but this one in green works for a simple demo. And you need to remember to set up that Singularity Pro module. Really essential that you have that or it won't work right. And so the other one, Conda, is a bit of a different idea of putting in your own Conda code. We have a whole webinar on setting that up, and I can try to remember to get a link, or maybe we can put that link in the chat before today ends. But Peter Rose has a whole session on setting up your Anaconda environment on Expanse. And again, there's times just when that's what you need. And so playing with them and learning about them is a good way to figure out what would work well for your application. And you wrap up by telling it where you want to start and what you want, a notebook or a lab. And that's pretty much it. So thank you for your time.